electrophilic addition reactions involving halogens. So that would consist of taking a double bond or an alkene and treating it with bromine or chlorine. The fluorine doesn't work for us because it works too well in that the reaction's explosive. So it doesn't do us any good because we can't control it. It just reacts so fast and it's not controllable. Iodine, on the other hand, reacts very, very slowly and is just not energetically favorable. So those two halogens, they're off the table. There's no need to even talk about them when we're looking at a addition reaction with an alkene and a halogen. It's only these two. And when we do that reaction, okay, in a solvent, let's say carbon tetrachloride, that's just our solvent, we are going to get a racemic mixture. Okay? We're going to add two halogens across this double bond. And we're going to generate something that looks like this, plus this. And that's a racemic mixture here. We do not generate this compound. So what do we see in here? With respect to this ring, you can see that the two products that are formed, one halogen is a wedge, and one is a dash. One wedge, one dash. And so those two products, the bromine is adding in an anti-fashion. Those bromines are not on the same face of that molecule. They're on opposite sides of that molecule. Whereas this product right here is a syn addition, because both these bromines are attached to the same face. And so another way we could say it is that that's syn addition because those substitute or those halogens are cis, and these right here are trans to one another. All right. So what's interesting is we only get these two. We don't get any syn addition. So the mechanism is going to help us figure out why we don't see any of this product. Mechanisms are so cool. They help us understand so much here. So why don't we see syn? Why do we only see the anti-product? Well, what we can do here to help us understand this is I'm going to take this molecule here and orient it. I'm going to rotate it 90 degrees. Okay, so we'll just rotate it, and now it's going to look like this. And then I'm going to take that molecule that's represented by my hand because it's in the plane of the glass. I'm going to rotate it 90 degrees. And so when I rotate it 90 degrees, I'm trying to represent that by making it really flat. Okay? And these structures are not the easiest to draw. What I will do my best. Okay. And we still have our double bond there, okay, like so. So I'm just trying to take this ring right here, rotate it 90 degrees so it's sticking out. These bonds right here are sticking out at us. Okay, so I'm making them a little bit thicker to illustrate that they're rotated. Okay? And I think that marker is near done. So now what's going to happen is the halogen can approach from either face. It can approach from the bottom face or the top face. I'm going to focus it attaching just from the top face, just for ease of drawing this. Okay? But what's happening here is that this bromine right here, okay, has some lone pairs. But when bromine gets really close to another electrophilic species, when bromine gets really close to another electron-rich species, bromine is very polarizable. And so what you're going to generate is a bromine that looks like this. This side of the bromine molecule is going to be partially negative, and this side is going to be partially positive. Okay? And what that does is that makes this bromine electrophilic. And so what we have going on here is that the pi electrons, electron-rich, can come in and attack the bromine. Okay? But bromine does, in fact, still have lone pairs that they're going to generate and come down and form that. And so what we generate here in this electrophilic addition step that electrophilic addition step, we are going to generate what's called the bromonium ion. Okay. And so what we have here is, try to draw this here the best way that I can. Okay. We have our bromine there, like that. And so that's in the front. Okay. But now what we have here is a halogen that has two bonds, so it's going to be partially positive. Now we need to take a look at what's happened here. Is that, you see how I only have one bromine here? What happened to this bromine? Well, what happened to it is I missed one mechanistic arrow here. So that's going to break like that. Okay? So now we have floating around our bromide. And let's put those back right there. Okay. So we have what's called the bromonium ion intermediate. And if you were doing this reaction with chlorine, you would have called it a chloronium ion intermediate. So let's write that out, okay? So that is our bromonium ion right there. Now this bromide right here now is going to do a SN2 attack, okay, to give us our product. All right? So if we want to go to this from here to there, we need to do an SN2 style mechanism. So we're going to take the bromide, okay, just making sure this looks right here. If I rotate that, and the bromide comes in and attacks. The bromide would come in and attack here, breaking the carbon-bromine bond, putting the electrons back. And now, so this bromine right here, okay, is this one right here. And now you can see that this is an SN2 style because this carbon-bromine bond right there is the leaving group. This bromide is the nucleophile, so it's going to come in on the opposite face of where the bromonium ion bromine is. This is on the top face, so the bromide has to attack from underneath to give us this. All right? So what if we wanted to go make this product? then it would be the exact opposite. This bromide would now decide to come and attack this carbon and then break that carbon. That would then give us this product. Because remember, this is a ring here. We have the bromine on top. So this bromide has to attack from underneath. And it has options. It has this carbon or that carbon. And so we have a 50-50 chance of which ones it will attack to give us this. Okay? Now, why do we not generate any of this? Because we're invoking an SN2 mechanism. In order to get syn addition, this bromide would have to attack from the same face that this carbon-bromine bond is breaking. So on top. And that cannot happen because the leaving group has to leave, whereas the nucleophile comes in from the opposite side or backside attack. So that is why this mechanism that I'm going to show right now is 100% wrong, because what it generates is a carbocation intermediate. So if we take our alkene above here and then do this mechanism like this, please note this is 100% wrong. Let's say if we do this and go like that, we would then generate something that looks like this. Okay. Let's say it added to the top face. That would then generate a carbocation. And so that bromide could, in theory, attack from the back face to give us one of these guys, or this one. So that's a possibility. But we know this mechanism is wrong because we don't see any of this. In order to get this product, this bromide would have the same probability of attacking from the top face. And if it attacked from the top face, we would go and generate that product. But because we don't see any of that in our reaction flask, we know that this mechanism at the bottom here cannot be. It's not possible. That mechanism does not work. We only see these two products. But if this was a true mechanism, we would see that product in the flask, but we don't. So we have to come up with this mechanism that I showed you at the very beginning, generating the bromonium ion intermediate or the chloronium ion intermediate. All right? So in conclusion, what this reaction right here will only give you the anti-product, no syn addition.